Hello, welcome to this talk on MIRAGE, mitigating conflict-based cache attacks with a practical fully associative cache design. My name is Gururaj Saileshwar, and this is work done with my advisor Qureshi at Georgia Tech. In this talk, I will tell you three things. What are set conflict-based cache side channel attacks? Why recent defenses have successively been broken with newer attacks? And how we design MIRAGE in a principled manner to eliminate current and future cache attacks. Processor caches help improve performance by allowing fast access to cached data and avoiding slow accesses to DRAM. However, the timing difference between a cache hit and a cache miss can lead to timing side channels, a security problem. In this talk, we focus on shared last level caches because they are shared across multiple cores and security domains. To enable efficient lookup, caches are split into small groups of addresses called sets. Addresses that map to such shared sets can evict each other from the cache. The classic prime and probe attack exploits sharing of cache sets by first having a spy fill a cache set with its addresses, allowing a victim to execute and evict one of the spy's addresses, and the spy, by observing a miss for its address, can infer that the victim accessed that cache set. If the address accessed by the victim was dependent on a secret, the spy can also infer the secret. This classic attack has been known for more than a decade and used to leak secrets like AES or RSA keys, user data like keystrokes, confidential ML models, etc. A key requirement of all such attacks is the discovery of a minimal set of spy addresses that conflict with the victim address and evict the victim address from the cache. Such a set is called an eviction set. This process is made harder with randomized cache defenses. These defenses use randomized mapping of addresses to cache sets to obfuscate the locations of set conflicts and make eviction set discovery harder. However, recent defenses have been broken by newer attacks. Let's see why. It all started in 2015 Oakland, where eviction sets were shown to be discoverable in order of n square accesses for a cache with n lines. For a typical LLC, this means eviction sets can be discovered in less than a second. Caesar in 2018 proposed randomized mapping of addresses to sets and dynamically changing this mapping before an eviction set can be discovered. While this prevents previous eviction set discovery algorithms, new attacks were shown to discover eviction sets faster in order of n accesses before Caesar can complete its remapping, thus breaking its defense. Subsequent defenses increase the level of obfuscation with multiple randomizing functions, one per partition or skew, and mapping new addresses probabilistically in one of these skews. While this made exact eviction set discovery harder with previous algorithms, new attacks showed that probabilistic evictions could nevertheless still be discovered on these defenses, thus even this defense was broken. The main reason why these defenses are broken is because they continue to have set conflicts at few locations. So despite the obfuscation, there is always an opportunity for an adversary to discover these locations and launch conflict-based attacks. So the only fundamental way to eliminate conflict-based attacks is to eliminate set conflicts, which brings us to our goal. For principled security, our goal is to provide the abstraction of a fully associative randomized LLC. What this means is when a new line is installed into the LLC, it can evict any random line from the entire cache, thus eliminating set conflicts. But designing such a cache is challenging. A naive approach to provide this abstraction would allow an address to map to any location in the LLC in a fully associative manner to evict any address. But this is impractical for an LLC, as a cache lookup now requires searching through hundreds of thousands of addresses in the LLC, which can be extremely slow, even slower than a DRAM access. Ideally, we prefer a traditional set associative design where lookups require searching through only 16 to 32 locations within a single set. So the key challenge is, how do we get the security of a fully associative design with practical set associative lookups? Our key insight is that we use results from well-studied load balancing problems to eliminate set conflicts. We model the behavior of our randomized LLC using the buckets and balls problem. Here balls represent cache lines and buckets with W capacity represent cache sets with W ways. When you install a line into the LLC, you evict a line. Similarly, each time we randomly throw a ball into a bucket, we also remove a ball to ensure that the total balls in buckets equals the cache capacity. When a ball needs to be removed due to a bucket overflow, it is equivalent to a set associative eviction. Our goal is to minimize these bucket overflows or set associative evictions. Let us consider a setting where infinite balls are randomly thrown with replacement into 4 buckets storing 16 balls. You'll likely have a bucket overflow every ball throw. Now if you have the same number of balls but in buckets with twice the capacity, bucket overflows can actually be avoided on ball throws. Now on each ball throw, the ball to be removed can be randomly chosen from among all the buckets, and any correlation between the bucket where the ball is installed and from where it is removed can be prevented. But there is still some possibility of bucket overflows due to skews in ball distribution. But instead of one random choice, what if we had 2 random choices of buckets for each ball throw, and we always pick the bucket with the lower load? This can lead to a very balanced distribution of balls as it avoids buckets with high loads. In fact, Mitzenmacher in 96 theoretically showed that with this power of 2 choices, bucket overflows can be made extremely improbable with sufficient over-provisioning of buckets. Using theoretical models and Monte Carlo simulations, we calculate the frequency of bucket overflows shown here on the y-axis in log scale as the extra capacity per bucket increases, shown here on the x-axis. We notice a super exponential curve. With each unit increase in the bucket capacity, the number of ball throws per bucket overflow gets squared. So in 5 to 6 successive squarings, we reach a situation where 1 bucket overflow is seen every 10 power 34 ball throws. In terms of our LLC terminology, an LLC with 75% extra capacity and power of 2 choices indexing has a security guarantee of 1 set associative eviction every 10 power 34 LLC installs. In layman terms, this means 1 SAE per 10 power 17 years, which is higher than the lifetime of the universe. Now that we know the security benefits of over-provisioning the cache and power of 2 choices indexing, let's see how we enable these features practically in Mirage. In a traditional cache, there is one-to-one correspondence between entries of the tag store, which stores the metadata, and the entries of the data store, which stores the actual data. So to over-provision entries inexpensively, we notice that extra tags are cheap, but extra data is expensive. So Mirage decouples these 2 structures and uses pointers to associate tags with arbitrary data entries. This allows Mirage to only over-provision the tag store with extra invalid tags while retaining the same data store structure. So if a new line is installed in such an invalid tag, it can be mapped to any random data store entry, and it can evict the data and the tag of any randomly selected line from the entire cache without a set associative eviction. This holds true only as long as an invalid tag is available in an indexed set. Next, to ensure the availability of invalid tags in index sets, Mirage uses the power of 2 choices indexing. Here, the tag store is split into 2 partitions or skews, and a new address is mapped to a random set in each skew using cryptographic set indexing functions. As a new address is always installed in the set with lower load between the 2 index sets, this ensures a balanced distribution of valid tags across sets and guarantees the availability of invalid tags in at least one of the indexed sets. With this, a new line is always installed in an invalid tag, and it evicts a random cache line identified from the data store without requiring a set associative eviction. This security guarantee is provided for the lifetime of the universe, and this eliminates conflict-based attacks in Mirage. Mirage also has protection against shared memory-based attacks like flush reload or flush flush, which exploit hits on addresses shared between a victim and a spy. Note that randomization alone cannot prevent against such attacks, as addresses shared between security domains can have a single shared cache line on which cross-domain hits are observable. Mirage uses the domain ID as an input to the randomizing set index derivation function, to ensure duplicate copies of such shared addresses exist across domains by mapping these addresses to different cache sets for different domains with a high probability. Additionally, it also stores the domain ID of an address along with the tag to ensure the cache line also gets duplicated across domains even if they map to the same set. This duplication of shared cache lines across domains ensures shared memory-based attacks are also eliminated in Mirage. Next, we discuss the results. We simulate an 8-core 16MB LLC system using a trace-based simulator and calculate the normalized performance versus a non-secure baseline. We evaluate the performance of Mirage and Scatter Cache, the previous state-of-the-art design whose security was recently broken. Overall, Mirage only incurs a slowdown of 2% due to the randomization and is quite comparable to Scatter Cache with 1.7% slowdown. Mirage also requires an additional 20% storage due to the extra tags, but a storage-neutral performance evaluation shows that Mirage is only 3.5% slower compared to a non-secure design with similar storage and higher capacity. In the paper, we also show Mirage Lite design that can reduce the required storage overhead while retaining a permissible level of security. We also provide additional results in the paper, including impact on LLC misses, lookup latency, logic overhead, and results with RISC-V and Gen5 implementations. In conclusion, Mirage is a principled secure cache design that eliminates cache attacks which leak victim addresses. It has strong security benefits of not having a single set associative eviction even in the lifetime of the universe, and these benefits come with modest costs. If you're interested, the code for the Gen5 implementation of Mirage, which passed artifact evaluation, is available on GitHub, and please reach out if you have any questions. Thank you.